Welcome friends, Igor is here, and in this video we will discover properties of matrix multiplication. In this lesson we will establish several properties of matrix multiplication, and we will realize that not all properties of multiplication of numbers apply to multiplication of matrices. Let's get started. To give you a little taste of what's to come in this video, let's immediately observe that matrix multiplication is not commutative. There are many reasons why matrix multiplication fails to be commutative. For example, one product A times B can be defined, but another product B times A may not be defined. The second reason is that both products may be defined, but they may have different size. Finally, even when both products are defined and they have the same size, for example, this happens when both matrices are square matrices of the same size, you still usually get different results when you multiply A by B and then B by A. This observation tells you that you have to be extremely careful with matrix multiplication. You cannot apply your old existing knowledge to this operation. You can only use those properties that we are going to formally prove. Let's define the zero matrix as a matrix all of whose entries are equal to 0. And the first property of matrix multiplication is that the zero matrix is an analog of zero number, in the sense that when you multiply any matrix with the zero matrix, the result is the zero matrix. The only caveat in this case is that the size of the zero matrix may change. Please inspect carefully both equalities to make sure that the products are defined given the proper size. I'm going to prove that property 1 holds, and I'm going to leave property number 2 as an exercise because it uses a similar reasoning. First, we of course check that the size of the matrix on the left-hand side of the equation is the same as the size of the matrix on the right-hand side of the equation, and then we proceed to comparing the entries of the matrix. To compute the value of the entry in position ij of the product matrix, we will use the entry by entry formula that we derived in the previous video. The entry in position ij of the product matrix can be computed by taking entries from row I of the first matrix, this is the matrix A, and entries in the column J of the second matrix, which is the zero matrix in this case, and then taking the dot product of the two lists of numbers. But every entry of the zero matrix is equal to the zero number, and of course when you multiply any numbers by zeros, you'll just get zeros. You add up a bunch of zeros, you still get a 0, and 0 is the entry in position ij of the zero matrix. This tells you that the two matrices have identical entries and therefore they're equal. Next, we are going to prove that the identity matrix is the analog of number 1 in the sense that any matrix multiplied with the identity matrix remains unchanged. Please pay the careful attention that depending on the side on which we multiply the matrix A, we may have to use identity matrices of different size. Again, I am going to prove only equality 1. The second one I'm going to leave as an exercise because it uses a similar argument. We compute the entry in position ij of the product matrix using the entry by entry formula. In this sum, where k ranges from 1 to n, I am going to pull out one term where k is equal to j. So that leaves one single term where k is equal to j, plus the summation of the other terms where k is not equal to j. The reason I did this is simple. The entry in position jj of the identity matrix is equal to 1, and the entry in position kj, as long as k is not equal to j, is equal to 0. This is how the identity matrix was defined. But now you see that the whole summation becomes just 0 and the entire expression simplifies to Aij. This is exactly the entry in position ij of the matrix A, and this shows that the matrix on the left-hand side of the equality has the same entries as the matrix on the right-hand side, and therefore they are equal as matrices. Next, we are going to prove the analog of the distributive property. We will show that matrix multiplication distributes over matrix addition. As in the other theorems, I will only prove the first property. The second one will use a similar argument. Let's compute the entry in position ij of the matrix A times the matrix B plus C. We think of this matrix as a product. It's a product of matrix A and matrix B plus C. So we use the entry by entry formula to represent the entry in position ij. We use entries from row I of the first matrix A and entries from column J of the second matrix, which is the matrix B plus C. Next, we use the definition of matrix addition. The entry in position Kj of the matrix B plus C is the entry in position Kj of the matrix B plus the entry in position Kj of the matrix C. Now we are dealing with numbers, and we do know that a multiplication of numbers distributes over addition of numbers. We then regroup the terms in this long summation and split this one long summation into two smaller sums. But now let's recognize that these are precisely the formulas for the entry-by-entry computation of the entries in the product matrix. The first sum is the entry in position ij of the matrix A times B, and the second sum is the entry in position ij of the matrix A times C. Using the definition of matrix addition, this is equal to the entry in position ij of the matrix AB plus AC. This shows that two matrices have identical entries and therefore they are equal. Next, let's show the associative property for matrix multiplication and scalar multiplication. In a sense, you're free to move the scalar multiple anywhere within the matrix multiplication. Again, I will prove the first equality and I will leave the second equality as an exercise. The entry in position ij of the scalar multiple of the matrix AB by scalar alpha is the entry in position ij in the matrix AB multiplied by the scalar alpha. This is the definition of scalar multiplication. Next, we apply the entry-by-entry formula for the entries in a product matrix. We take entries from row I of matrix A and entries from column J of matrix B. We are dealing with numbers now, and we know that multiplication of numbers distributes over addition. Next, let's notice that alpha times aik is the entry in position ik of the scalar multiple of the matrix A by the scalar alpha. But now you should recognize that the last summation is exactly the entry-by-entry formula for the entry in position ij of the product matrix, matrix alpha IA multiplied by the matrix B. This establishes that the two matrices have identical entries and therefore they are equal. Next important property is that matrix multiplication is associative. To prove that these two matrices are equal, we will prove that they have identical entries. Before we do this, please check that the matrix on the left-hand side has the same size as the matrix on the right-hand side. The entry in position ij of the matrix product, matrix A multiplied by the matrix BD, can be computed using the entry-by-entry formula. We take entries from row I of matrix A and entries from column J of the matrix BD. But now we are going to express the entry in position Kj of the matrix product BD using its own entry-by-entry formula. To compute this entry, we take entries from row K of matrix B and entries from column J of matrix D. in this case, I will use L as an index in the middle. The sum, as L changes from 1 to p, gets multiplied by the number aik, so we distribute this number inside the sum. And next, we are going to apply a standard trick when we work with double summations. What we are going to do is we are going to regroup the terms so that the inner summation happens along the index k and the outer summation happens along the index L. You achieve this by using the commutative property of number addition. You simply switch the order in which the terms appear in the sum. Next, let's observe that in the product of the three numbers, the entry from the matrix D does not depend on k, and because the inner summation happens along the index k, we can factor out the entry from the matrix D. Now, you should recognize that what we have inside the parentheses is the entry-by-entry formula for the entry in position IL of the product matrix AB. Now, we are almost done. To visually help you see what's going on, I'm going to apply the commutative property of multiplication of numbers. And now, you should recognize that this is the entry-by-entry formula for the entry in position ij of the product matrix AB multiplied by the matrix D. Now, if you look at the beginning and the end of this computation, you will see that the two matrices under question have identical entries. Therefore, they're equal. The last property tells us that transpose distributes over matrix product, but you have to change the order of the multiples. The transpose of the product matrix AB is B transpose multiplied by A transpose. To see why we switch the order of the matrices when we take the transpose, let's look at the sizes of the matrices involved in this equation. The matrix A has size m by n, and the matrix B has size n by p. Therefore, the product matrix AB has size m by p. When we take the transpose of a matrix of size m by p, it becomes a matrix of size p by m. This shows that the matrix on the left-hand side of this equality has size p by m. Let's look at the matrix on the right-hand side. B transpose is a p by n matrix. A transpose is an n by m matrix. Now you see why we can multiply B transpose by A transpose, but we might not be able to do it the other way around. Now, a P by N matrix multiplied by an N by M matrix is a P by M matrix. And so now you see that the matrix on the left-hand side and the matrix on the right-hand side have the same size, and the size is P by M. Of course, the size comparison alone does not tell us that the matrices are equal. For this, we need to look at the individual entries. The entry in position ij of transpose of the matrix AB is the entry in position ji of the matrix AB. This is the definition of the transpose of a matrix. Next, I'm using the entry-by-entry formula to express this using row j of the matrix A and column I of the matrix B. Let's use the property that multiplication of numbers is commutative and switch the entry of the matrix B and the entry in the matrix A. Next, let's observe that the entry in position ki of the matrix B is the entry in position ik of the matrix B transpose, and the entry in position jk of the matrix A is the entry in position kj of the matrix A transpose. The last step is to recognize the last sum as the entry-by-entry formula for the entry in the product matrix B transpose times A transpose. This is the entry in position ij of this matrix. Now, if you look at the beginning and the end of this computation, you will see that the two matrices under question have identical entries and therefore they're equal. To conclude this lesson, let me indicate several other properties of multiplication for numbers that do not extend to multiplication of matrices. We already observed at the very beginning that matrix multiplication is not commutative, but this is not the only property of multiplication of numbers that fails for matrices. For example, we have a cancellation law for numbers which says if alpha beta equals alpha gamma and alpha is a non-zero number, then you can cancel it and then beta will have to be equal to gamma. Also, if you have a product of two numbers equal to zero number, then at least one of the numbers must be equal to zero. In abstract algebra, this phenomenon is called there are no zero divisors. However, these properties do not hold for matrices. So please come up with explicit counterexamples which show the following. It is possible for the product matrix AB to be the same as the product matrix AC. Moreover, A is not the zero matrix, because zero matrix is the analog of the zero number for matrices, yet the matrix B is not the same as the matrix C. So you cannot cancel non-zero matrices from the products. Moreover, it is possible to multiply two non-zero matrices and get a zero matrix. Let me give you a little hint. Look for simple examples within 2 by 2 matrices. You can construct all these counterexamples for these small 2 by 2 matrices. And please write down in the comments below which examples you come up with, because there are many different examples you can use to illustrate how these properties fail. If you found this video useful, please give it a like to help others discover this content, and subscribe to this channel to see more of these videos. In the next video in this series, we will define matrix inverses and we will learn how they can be used to solve linear systems. I will see you later.